Alright, so we got a series here. And to determine whether or not it is converging, we're going to use the alternating series test because it is clearly alternating. It's being multiplied by -1, then 1, then -1, then 1, then -1. And the hypotheses that are required to be satisfied to do the alternating series test are the following: alternating, check, decreasing, let's see. Actually, we'll do the limit as, because this is another requirement. In approaches infinity of absolute value of that is going to be n squared over n squared plus n plus 1. And we'll divide by times 1 over n squared, the biggest power, times 1 over n squared equals the limit as n approaches infinity of 1 on top, because n squared divided by n squared is 1. And then we'll have 1 in the front, divided by n squared divided by n squared is 1, plus 1 over n, because n divided by n squared, cancel that 1 in, and that equals 1 over n. And then for the last part, it's just obviously 1 over n squared. This is equal to, this approaches 0, this approaches 0, as n gets really large, and this is equal to 1, because you just are left over with 1 over 1, which is not 0. Therefore, first of all, our hypotheses are not satisfied because it's not equal to 0, which is required by the alternating series test. I should write that. Alternating series test, AST. Implies, therefore the series is divergent. This is not because it did not meet the hypotheses of the alternating series test. The reason it is divergent is because it satisfies the hypotheses of the divergence test, because the limit of as n approaches infinity of a of n is not equal to 0, i.e. by divergence test. This is the most basic test, because if you're adding up term after term after term after term, and those terms aren't getting small, or they aren't going to 0, then you're adding up a non-zero number an infinite number of times. So that is obviously going to be a divergent, or an infinite sum, or the sum would be infinity, which is not convergent, it is divergent, and that's our answer.